Hi, my name is Eduardo Longa, and I'm a postdoctoral researcher at University of São Paulo. And this is the first part of a two-part video that I'm recording for the third Geometric Analysis Festival. First of all, I want to thank Hojo Lee for inviting me to record these videos and congratulate him on this wonderful initiative of this Geometric Analysis Festival. So the topic I want to address today is capillary minimal surfaces. So this is a brief outline of the talk. In the first part of the talk, I will present some basic concepts on differential and Riemannian geometry and some basic notation for everybody to follow up the talk, and also presenting some definitions on capillary minimal surfaces, CMC surfaces, stability, and so on. In the second part, I'll present some known results concerning capillary minimal surfaces in three manifolds and some results in higher dimensions. And finally, in the last part of the second talk, I'll present some results I proved in my PhD thesis. So let's start with the first part of this two-part series. And in this first part, I'll present some basic concepts and notation concerning the Riemannian geometry and differential geometry. Okay. So in the remaining of the talk, we will be treating about surfaces on three manifolds. So although the definitions I give here were for more general settings of higher dimensions, I'll just keep the dimension low so we can grasp more the abstract notions. So let's fix a Riemannian three manifold, and we denote by number the Riemannian connection of M. This is very known to exist for every Riemannian manifold. And we denote by R its Riemann curvature tensor. So it's a tensor that takes two vectors and another vector and produces a fourth vector. So this is the Riemann curvature tensor, and we say that M is flat whenever R is identically equal to 0. This means that M just looks like the Euclidean space, wherever R is equal to 0. After defining Riemann curvature tensor, we can talk about the Ricci tensor, which is a weaker notion of curvature. It's a kind of mean of all sectional curvatures of M with respect to a fixed direction. It's a 2-0 tensor, but we can fix, for example, x equal to y and define a kind of quadratic form. So this is the Ricci tensor. E1, E2, and E3 is a local orthonormal referential for M. And the definition does not depend on the local orthonormal referential. So this is the Ricci tensor. And more general still, we can talk about the scalar curvature of a Riemannian manifold, which is a very important notion in recent days, mainly due to the very interesting questions asked by Mikhail Gromov. And this scalar curvature is the trace of the Ricci tensor. So it's given by this nice formula here, where E1, E2, and E3 is just like before, an orthonormal referential. Great. This will be important in the talk, so keep in mind this notion. So What I talked before was about global geometry of M. If we now restrict to immersions of smooth surfaces on M, we can still define other notions that depend on the immersion. So let's fix a smooth surface, sigma, and a two-sided immersion phi from sigma to n to m. So this is just a differential map, which is whose derivative is injective at every point. And by two-sided, I mean that the normal bundle of this immersion is trivial, which means that there exists a global defined unit normal vector field for sigma along phi. So this is a vector field on sigma along phi. So for every point of sigma, and p, for example, n of p is orthogonal to the tangent space of sigma via phi. So the curvature of sigma inside M can be measured mainly through this bilinear form, which is called the second fundamental form of sigma. This is the second fundamental form. This is a bilinear form on sigma. He eats two vectors and throws out a third vector, and basically the derivative of the normal vector field. And this operator, which is the derivative of the normal vector field, is called the shape operator, which will be in the sequel. And we say that sigma is totally geodesic whenever A is identically 0. So this means intuitively that sigma doesn't curve inside M, or that geodesics of M that start tangent to sigma stay tangent to sigma whenever they are defined. Great. So as I was saying before, the shape operator of sigma is this derivative of n in an arbitrary direction of the tangent space of sigma. There's a little mistake. X should be tangent to sigma there. And the mean curvature, which is a very important concept and will be very important in the sequel, is just a trace of this operator. So it's the sum of its two eigenvalues, lambda 1 and lambda 2, which are called the principal curvatures of sigma. So this is a mean curvature. And we can also say some definitions for the boundary of M, if M has a boundary. For example, if M has a boundary and the mean curvature of the boundary is positive, then we say that M has mean convex boundary. And if the mean curvature of the boundary is just non-negative, then we say that the boundary, the manifold is weakly mean convex. Also, if the second fundamental form of the boundary is a positive definite bilinear form, then we say that M has a convex boundary. And if it's just non-negative, it's positive but not necessarily definite, we say that M has a weakly convex boundary. Okay, these were the definitions we need for following up in this talk. And in this next part, I'll say a few words about capillary surfaces and their motivations and some examples and how to define them properly. So, capillary surfaces, as I said in the introduction video, they arise as the interface between a fluid and the air, where the fluid is in a thin tube, which is called a capillary tube, hence the name capillary surface. So as you can see in this picture here, at the left, picture A, the surface that forms in the interface makes an angle, a constant angle with the boundary of the tube. And this is called the capillary angle of the surface. In this case, is shown as theta. And in physics, they can calculate the height that the liquid moves up just in terms of known quantities, such as the radius of the tube, the density of the liquid, and other factors, like the gravity, for example. It's an interesting property that the angles that water make with the boundary of tubes and mercury makes with the boundary of the tube, they are different, of course, because they are different liquids, but not only different angles as in water they are acute angles, with mercury they are obtuse angles. So the material really determines not only the material, but the material heavily influences the angle of the capillary angle with the boundary of the tube. So there are very known examples of capillary surfaces, and the most common ones are called free boundary surfaces, which are minimal surfaces that intersect the boundary of your ambient manifold in a right angle. So, for example, in figure A, we see an equatorial disk. It's a flat disk in a ball, in a unit ball of R3. And so it intersects as a free boundary minimal surface in the ball. And in figure B, you can see a sort of foliation of the ball by free boundary minimal surface, free boundary CMC surfaces, which intersect the boundary, of course, in right angles. But you can slide this picture to make an arbitrary angle between 0 and pi to happen. So, for instance, if you take an equatorial disk and slide it upwards so that it doesn't contain the origin anymore, then it intersects the boundary of the ball in a different angle, and it may be constant if it's parallel to the XY plane. So this gives an example of a capillary minimal surface with an arbitrary angle between 0 and pi. Another very famous example is the catenoid in the ball. So this is a minimal surface of rotation in R3, and we take the part of the surface that is contained in the ball. It's a free boundary minimal surface, but it lies inside a family of surfaces. If we multiply in R3 by a number, the vectors by a number, you make a homotopy in R3, then the catenoid belongs to a family of one parameter family of surfaces that intersect the ball in different angles. There we obtain a family of capillary minimal surfaces. We also have these beautiful pictures that I took from Alessandro Carlotto's website of genus 1 and genus 2 free boundary minimal surfaces in the ball whose boundary is connected. So it's a very beautiful picture of other types of surfaces of higher genera. So there's an incredible amount of examples. The free boundary examples are certainly the most common, but there are also many other examples where the angle is not necessarily pi over 2. So having these examples in mind, we can go through the proper definition of what a capillary surface is. And I like to use the variational properties to define what a capillary surface is. You will see in a moment. So let's fix a three-dimensional oriented Riemannian manifold with boundary. Now they have boundary. And fix sigma, a compact connected smooth surface with boundary. Let's also fix two-sided immersion, phi, which is proper. And by proper, I mean that the boundary of sigma intersects only the boundary of M. There is no interior point lying in the boundary of M, and all the boundary of sigma is mapped by phi into the boundary of M. This is what I mean by proper. So associated to this data, I have 4 vector fields which are very important in the theory. So we have N, which is normal to phi and exists because the immersion is two-sided. We have nu, which is the outward core normal for the boundary of sigma inside sigma, so it's tangent to sigma. We have n bar, which is the outward normal for the boundary of the ambient manifold M. And we also have nu bar, which is the conormal for the boundary of sigma now inside the boundary of M. So if you have a closer look, then there are 2 different orthonormal bases here. N and nu form one basis, and n bar and nu bar form another orthonormal basis. And since there are 2 choices for nu bar, we choose nu bar such that these 2 bases determine the same orientation on the orthogonal complement of the boundary of M, the boundary of sigma, inside the tangent bundle of M. So these vector fields are very important. And we now want to perturb the immersion sigma phi so that we can define what a capillary surface is by means of a variational approach. So we say that a variation of phi is proper if each of the instant maps phi t, where we fix the second variable t, is a proper immersion. So phi is always smooth, we always consider it to be smooth, and we will always consider it to be proper as well. Great. So associated to this variation, there is a fundamental vector field called the variational vector field, which I denote by psi, that shows at time 0, at every point of sigma, the instant velocity at which the variation is moving the immersion phi at time 0. So formally, this means that the map psi is just the partial derivative with respect to t of this map x, of this map phi at 0. So this is a vector field on sigma along the immersion phi. Phi is always fixed, small phi. Great. So we can define various functionals associated to this variation. And the first one is the area functional. It just measures the area of each perturbed surface. So formally, this is an integral of the area element of the pullback metric by the immersion phi t. We also define the volume functional, which is the signed volume that the immersion makes, the perturbed immersion makes with respect to the initial immersion. And it's just this formula, the pullback of the volume element of M, and you integrate it in the product manifold. And we say that the variation preserves volume if V of t is equal to 0 for every t. So this is a natural condition to ask if you want, for example, in a tube, that no liquid spills out of the tube and we remain always with the same amount of liquid as we move, as we shake the tube. So a variation is just shaking the tube and showing the perturbed interface of the liquid with the air, and we say that phi preserves volume if we don't lose any liquid in the process. Great. So finally, we define this wetting area functional, which is basically the signed area in the boundary of the tube that the perturbed surface makes with the boundary of the initial immersion. So this is why we call it the wetting area. So just the part of the tube which is being wetted by the liquid when we shake it. And we define finally the energy functional we are interested in, which I call E theta, which depends on an angle theta between 0 and pi. And we define it as this quantity here is the area functional minus the cosine of theta times the wetting area functional. Notice that when theta is equal to pi over 2, then this energy functional is identically equal to the area functional. And so we take back the theory for free boundary minimal surfaces, where we study the area functional. So we can make a lot of stuff with this energy. For example, we can calculate the first variation, which is the first derivative at time equal to 0 of E theta along a proper variation of fixed immersion phi. And it's given by this nice formula here. It involves the mean curvature H of the immersion, the variational vector field psi, those fundamental vector fields I presented before, nu and nu bar, and also F, which is a normal component of the variational vector field. So if you have a closer look, a critical point of this energy functional for every proper variation, we define it to be a capillary minimal immersion. And if you have a closer look, it means that H has to be equal to 0 because F can be made arbitrary, because in its turn, psi can be made arbitrary because the variation is arbitrary. And also the angle between n and n bar is equal to theta, which means that the surface intersects the boundary of the ambient manifold in a constant angle equal to theta. So a critical point is called a capillary minimal immersion with contact angle equal to theta. Theta is always referred to and is part of the definition of a capillary minimal immersion. Similarly, if we only require critical points for E theta for every volume preserving proper variation, then we have the notion of a capillary CMC immersion. And just like before, we see that this happens exactly when the mean curvature of the immersion is constant and the angle that the normal of the surface with the normal of the ambient manifold make is equal to theta. So this is the definition I like, instead of just giving this last part, a capillary minimal immersion is just a minimal surface which intersects the boundary in a constant angle. Yes, but we can say more, they can be characterized as critical points of an energy functional. And this is what I want you to carry for you. Nice. So let me fix now this double I, which is the second fundamental form of the boundary of the ambient manifold with respect to minus n bar. So it's given by this formula here. So we have the second variation of energy. And the second variation of energy shows here a Jacobi operator of sigma. It involves the Jacobi operator of sigma, which is a kind of elliptic operator of second order in sigma, which is given by this nice formula. It's the Laplacian of sigma plus a scalar function, which is the Ricci in the normal component, plus the normal of the second fundamental form squared. So this formula, you don't have to memorize this, But I want you to keep in mind that the second variation of energy involves the Jacobi operator of sigma, and also this function Q, which is given in terms of the second fundamental form of sigma, sorry, and the second fundamental form of the boundary of the n-bit manifold. And notice that when theta equals pi over 2, then we have the usual second variation of energy for free boundary minimal surfaces. This is an exercise. So given this second variation of energy, we can introduce the so-called index form of sigma, which is the bilinear form in H1 of sigma, where H1 is the first Sobolev space of sigma. And it's given by this formula here, which kind of resembles the Jacobi operator in the first term, and the second one is the L2 product. This index form is the bilinear form associated to the second variation of energy functional. And we can define the stability index of minimal or CMC immersion as being the maximal dimension of a subspace of H1 such that this form Q is negative definite. So it's the largest space on which Q is negative definite. And it can be proven that this is a non-negative integer. I mean, it's not infinite. It's always a finite non-negative integer. And it should be remarked that we have to take care in which vector space we have to take the linear subspaces. If we're talking about capillary minimal surfaces, then we have to take S in this definition as being the full H1 of sigma. Whereas if we are talking about capillary CMC surfaces, then we have to take S as being those functions in H1 whose mean is 0. Okay, so this is the stability index of sigma. It's a non-negative integer. Intuitively, it measures the number of different directions we can perturb sigma so as to decrease its energy by a second order approximation. If we were talking about free boundary minimal surface, then the index would intuitively mean that it's the number of different directions we can, independent directions we can perturb sigma to decrease its area, not energy. But now we're talking about energy, and the energy involves not only the area, but that term which is the wetting area. So having this definition in mind, we say that the immersion is a stable capillary minimal immersion. Well, first, if it's capillary minimal, of course, and if its second variation of energy is non-negative for every proper variation. So it means that in whatever way we perturb sigma, the energy does not decrease up to second order. And if it's called a stable capillary CMC immersion, if it's, of course, capillary CMC, and also the second variation of energy is non-negative now for every volume preserving variation of phi. So we just require that the variations now are volume preserving. Nice. So equivalently, this means that the index of sigma, according to the previous definition, is just equal to 0, because there are no subspaces other than the trivial subspace on which Q, the bilinear form Q, is negative definite. So this is the first part of this two-part series, small series, and in the next part we'll see some results concerning some theorems concerning these capillary, minimal, and CMC immersions, and I will show you some results I obtained in my PhD thesis. And so I'll see you in the next video. Thanks for watching.